Welcome everyone. It's my greatest pleasure to have Vijay Vazirani here. Vijay was my PhD advisor, uh, and more than that, he's made seminal contributions to the theory of algorithms, uh, some really kind of outstanding and seminal work on matching, approximation algorithms. He literally wrote the book on it. And for the last couple of decades, he's made fundamental contributions to algorithmic game theory and economics. And today he's going to tell us about something that involves both matching and game theory, the stable matching problem. So without further ado, over to Vijay.
Oops. Right. So thank you all for coming. Very difficult to match this onto my belt, but okay, I'll put it in my pocket. Okay, so let me start by defining the stable matching problem. I think Yuval is supposed to be here soon, right?
Apparently there was a meeting.
Yeah.
Yes, that turns up.
Okay, we'll see. Okay, so everybody here has heard of the stable matching problem. If not, let me just give you a quick reminder. So what you have in stable matching problem here is a 3x3 instance. You have n boys and n girls. So there are boys 1, 2, 3, and there are girls A, B, C. And each boy has a preference list over all the n girls, such as this is the preference list of 1, 2, and 3. And each girl has a preference list of all the n boys, so the preference list of A, B, and C. And we are going to look at all possible perfect matchings. There are n factorial of them. And some of them are good for us, some of them are not. I show you 3 matchings here. And right away, I'll tell you that these 2 are good, and this is not good. And the reason it's not good is that, now I should take a quick peek in my, 1A. So if you look at this pair, 1A, this boy and this girl, they're not married to each other, okay? But one likes A better than his mate, and A likes 1 better than her mate, right? So 1A is a pair that is not married to each other, a boy-girl pair that's not married to each other, and they like each other more than their own mates in this particular marriage. Okay, so they have very little holding them back in this marriage. They'll elope, get married somewhere else, right? And you'll be left with, dangling singles somewhere. That's not the way to keep stability in the household.
So why don't like those?
Huh? No. But you'll have one girl and 1 boy left, right? Okay, so that's why it's not stable, and this thing is called a rogue couple. You can call it a blocking pair. It's the formal name. So a stable matching is any perfect matching with no blocking pairs. Okay, I don't need to write down anything like that. You've seen this many times already if you're in computer science. So this. There was this seminal paper of Gale and Shapley, 1962, which defined this problem, and since then it's been studied by 5 or 6 different fields, not just one: computer science, discrete math, operations research, economics, game theory, maybe even biologists have studied it, I don't know, maybe, right? Yeah, so, and there's huge structural properties there, very pristine, beautiful, I mean, so beautiful that just about anything you think about, any question you think about, has a polynomial time algorithm. That only follows if you have good structure, okay? So, and it's been studied from many different angles. This work also got the Nobel Prize in economics in 2012. Gale had already passed away, unfortunately, but Shapley got it then together with Al Roth, who did a lot of work on incentive compatibility issues in this market, in the stable matchings, and also in kidney exchange and so on. So anyway, Shapley and Roth got the Nobel Prize in 2012. So this is, I mean, this is as beautiful as it gets. And you'll get a glimpse of that today for sure. Okay, so what am I going to talk about today? So it's been examined from many different viewpoints, and it's very difficult to think of another viewpoint, but looks like we did manage to think of another viewpoint, and that is the notion of robustness. So robust stable matchings. What is that? So think of the following scenario, that you have a channel, and in Venki's language, huh?
I don't know what I did.
In Venki's language, there's Alice sitting here and Bob sitting here. Okay. Okay. And Alice has an instance A of stable matching. By an instance, I mean all these 2n lists, right? And she sends it on this channel, which is error prone. It can create an error. Okay. And what Bob gets is some instance B, which is slightly perturbed version of A. And Alice also has, so by the way, here she's sending order n square numbers. Okay, so this is a lot of information, but she also has another error-free channel, which is thinner. It's green in color, so it doesn't include make any changes, no errors introduced. And on this, she transmits a matching M that is stable for A. Okay, and she knows there is a domain D from which errors are introduced. So the channel doesn't introduce arbitrary errors. There's a domain D from which it picks one error and introduces it into the instance. And I'll define what domain D is. And there's a probability distribution P on D, a discrete probability distribution. So the errors are picked from this discrete probability distribution. And Alice sends this matching also to Bob. And of course, she wants this matching to be stable for B also, right? And in fact, she would like to maximize the probability that matching M is stable for B. And that's what we call a robust matching. So it's M is robust, M belonging to the set of matchings that are stable for A, which I'll denote by M subscript M sub A, is robust if it maximizes the probability under this distribution P that M is stable for B. Is that okay?
That means that Bob has to correct errors given the.
No, Bob doesn't correct errors.
Come to a correct matching by himself?
No, M is transmitted error-free,
Okay.
and whatever he gets, he will just get M, of course, here. But here he'll get B. And if M is stable for B, he doesn't have to do anything, right?
B is the instance of
The instance that is perturbed
I see.
after going through this channel. So this A goes through like this, okay, and somewhere some change happens. Okay, I don't know where it happened, but only one change happens. Yeah.
Could we think of B as maybe like a time developed, like after some, like A?
It's very simple. You just introduce one error. Okay. So for instance, you may flip these two guys.
Sure. The point being, like, we want something that's still stable even after any changes made.
Yes.
Or as much as possible.
Yeah. So you want that M is stable not only for A but for also the perturbed instance B.
But in your definition, you want every matching to be.
No.
Because M can be anything. Like
No.
should you
Find A. Find M.
find one. Okay.
How can every matching be stable for B when B
Right,
has
right.
changed?
Okay.
And the error needs to be within contiguous.
I'll tell you what the errors are. So So I'll give you a class of errors under which we can solve this problem in polynomial time. Okay, I'll give you later. Okay, because there's a lot to be talked about before that. And for a certain domain D, and here the domain D is polynomial sized. Okay, and then there's another domain D. So this is theorem 1. So polytime algorithm. So efficient algorithm to get for finding robust stable matching, no matter what the probability distribution is. It's a discrete probability distribution. Okay. Theorem 2 is, under theorem 2, the domain D becomes exponential sized. Okay. So D prime is exponential, much bigger actually. Okay. To n 2 to the n. Okay, some exponential sized domain, and from this you pick some set S such that S is polynomially bounded, polynomially sized. Okay, and theorem 2 is any S. Okay, theorem 2 is efficient algorithm. In this case, efficient algorithm for finding a fully robust matching, stable matching. What is fully robust? So if so M is full robust if this, it is fully robust if it is stable for all these instances, polynomially many, inside S. If M is stable for A as well as these B1 through B polynomially many n's belonging to S. Okay, and S is arbitrary. Okay, so this is a weaker result, obviously. Fully robust is a stronger concept, but this is a weaker result because if there's no fully robust, you'll say, oh, I cannot find anything. Okay, so of course the big open question, one interesting open question is, can you, for this setting, can you get a robust stable matching? Anyway, so, but I have to give you the domains which I'll specify in a few minutes. But first, let me get into the structure of stable matchings. So, how many people here know that the set of stable matchings for an instance forms a lattice? Okay, so let me say define all those notions that I just mentioned in this sentence. So let's define a partial order on stable matching. So MA, so A is an instance, and LA not yet, MA, script MA is a stable matchings of this instance. They could be exponentially many, they could be polynomially many, it could be just unique. MA cannot be empty. We know that from Gale Shapley. Right. So we define a partial order on MA. So we say that M is less than or equal to M prime if every boy in M, every boy is weakly better off in M than in M prime. Okay? Every boy is weakly better off. Okay? So, yeah.
So when A sends and there's an error in B, when Bob gets an M, is there a notion of fixing B itself?
No.
So we don't
No,
we don't
no,
talk
no,
about that.
no. I just want to say, so why robust under errors in the input? So this is a big field within algorithms and within optimization. So when you have an instance, things get perturbed and errors get introduced. Can you get solutions that are robust to these errors?
I understood that.
Right?
In the other code, you try to correct it also.
Not,
not yet.
anybody can take it from here to anywhere. There are
You don't consider that.
there are so many avenues to start from here and do all kinds of things like that.
Okay.
Like if we talk about that, we'll just spend the whole hour.
That is probably not.
Okay. So no, literally there are so many questions that can be thought of. And because stable matching's robust solutions is so well developed a field, there are entire books written on it. And nothing has been done on this as far as we know. Okay. But I'll say a bit more a bit later. Okay, so take this partial order, and then define. So it turns out that so let's list these matchings so that the matchings here are better for the boys than the matchings here. The matchings here will correspondingly be better for the girls than the matchings there, okay? And I'll think of this as preceding, succeeding, above, before, okay, below. So take any two matchings, M1, M2, and find their lowest common predecessor. Turns out it's unique. There exists a unique lowest common predecessor. Okay, and there exists a unique highest common successor. And this I'll define as the meet of M1 and M2, and this as the join. And because this set MA with this partial order has both these operations meet and join, namely this uniqueness, therefore we say that there's a lattice. MA forms a lattice. Okay, and any lattice would have a unique highest element and a unique lowest element, and this is generally denoted M0, and this is called the boy optimal marriage, and this is called the girl optimal marriage. And similarly, this is also the girl pessimal marriage, and this is the boy pessimal marriage. Everybody gets their worst possible, every boy gets their worst possible girl here, and every girl gets her best possible boy, the best possible among all stable marriages. Everybody knows those kinds of theorems, right? So, and then if you take any two matchings M1 and M2, there's a meet and a join, okay? And because we are in stable matchings, the meet and the join have to be very beautiful, right? I'm not saying that the people there are beautiful. I'm saying the meet and the join themselves are beautiful, okay? So what is the meet and join of M1 and M2? Well, suppose that under M1, B got married to G1, and under M2, B got married to G2, then under the meet, so marry B to the better of M1 and M2. Or G1 and G2, what am I saying, right? And under the join, marry B to the worst of G1 and G2. Do this for every boy. Lo and behold, it will be a matching. Lo and behold, it will be a stable matching. And lo and behold, this will be the meet, and this will be the join. This will be the unique lowest common predecessor, and that will be the unique lowest common successor. Sorry. Okay, is that okay? Question? Okay. Okay, then comes along Conway, good mathematician, great mathematician, and he says that not only do these stable matchings form a lattice, okay, but that it's a distributive lattice. Okay, what does it mean that it's a distributive lattice? That means that meet and join distribute, and just the way that union and intersection distribute. And I don't have to write those formulae because you know what distributive property is, and it says almost nothing as you write it down. But I'll tell you how to really interpret it here. Okay, so this is what Conway showed or observed, and then comes along Don Knuth, and he asks, okay, so these are distributive lattices. And these are, of course, finite. But are all finite distributive lattices covered under stable matching lattices? Okay. In other words, do the stable matching lattices miss any finite, under isomorphism, of course. And somebody comes along, Blair, I think his name, and he shows that, yes, that if you look at all possible instances of stable matching and all the lattices generated by these instances, they are all the finite distributive lattices. Nothing is missed here. Okay? So lo and behold, we can apply some very nice properties of finite distributive lattices. And that's the only thing I want you to take back about distributive rather than the formula. And what is that property? That property goes back to 1937 due to Birkhoff. Have you heard of Birkhoff? Yeah, wrong one. Forget that one.
Birkhoff and Lane.
Huh?
This book, the book, Birkhoff and Lane.
No, that is the wrong Birkhoff. Think of his son. That's the Birkhoff we are talking about. Okay, not the Birkhoff von Neumann Birkhoff. Okay, so there's another Birkhoff, and he showed the following. Okay, to say what he showed, let me give you a definition. Let's take a partial order on some n elements. Okay, whatever n is, I don't care. So P is a partial order, and let me show it by an example. So it's a partial order on some elements. So let's say this is a partial order. Okay, this is a partial order on 3 elements. And now look at all the upward closed sets. That means that if a set S has an element alpha, then all its predecessors are also in S. Okay, and of that kind, you will find that the empty set is one of them, the set containing A is one of them, the set containing B is one of them, the set containing A and B is one of them, and the set containing A, B, and C is one of them. Okay, and if you look at these sets, this set of sets, these sets are closed under union and intersection. And these sets form a distributive lattice because the union and intersection distribute. And this is the most canonical finite distributive lattice. In this case, it will look like the following. Empty, the set containing A, the set containing B, the set containing AB, and the set containing ABC. Okay. And this will be called the lattice generated by the partial order P. Okay? And Birkhoff showed that if you take any finite distributive lattice L, then there exists a partial order P such that the lattice generated by P is isomorphic to L. Is that clear? The contents of this theorem? That any finite distributive partial order is isomorphic to the lattice generated by some partial order, which of course has a fewer elements. And let's see how many elements. Okay. Now, this being stable matching, of course, P also has to have very special and beautiful properties. Okay. And what are they? So what it turns out is that, and so I guess I can start erasing from here. So it turns out that the elements on which P is defined are called rotations, or some set R of rotations. And that's a very interesting, very deep notion in stable matchings. What's a rotation? A rotation with respect to some matching. So if you have M is a stable matching, then a rotation is some R boys and girls, B1, B2 through BR, G1, G2 through GR, sorry, such that they are married to each other. I mean, BI is married to GI, okay? And if you cyclically rotate the weddings so that you marry him to her, and finally him to her, you still get a stable matching. Okay, that's called a rotation. If when you took any subset of these R guys, R boy-girl pairs, any subset, take any order and do a rotation, you will get an unstable matching. So it's like a minimal change to lead to a stable matching. Leading to stability. Okay, and what happens is that you have this partial order on rotations, so P on R, okay, and so there is some partial order that may look something like this. It's always hard to draw. Oops. Better to draw all the edges going downwards. Okay, some arbitrary looking thing. So these are, it's a partial order on rotations R, and LA is the lattice generated by the stable matchings of instance A. It's going to be isomorphic to the lattice generated by this partial order, okay, in the following sense, that if I take a closed set S in this partial order, like the closed sets that I drew there, upward closed, okay, then that set has to correspond to some matching here, right? How is that matching obtained? What you do is you start with the boy optimal marriage and apply these rotations in a topological order. So in other words, you can apply this only if you apply all the predecessors. Apply these rotations in an arbitrary topological order. You will get a path from M0 to MS. And the various ways of applying rotations will give you all possible paths from M0 to MS. Okay? So that's what it is.
Partial order of rotations?
Some set of rotations. Now, good question is, how many rotations do you need in this partial order? Turns out that any boy-girl pair can be in at most one of the rotations in R. Okay, any BG belongs to at most one rotation. So the set of rotations is at most order n square. So this is a succinct representation of this potentially exponentially large lattice. And it generates all the matchings in this. Okay? And if you apply all the rotations in any order, starting from m naught, where will you get to? Huh? Yes, over all possible paths. So these rotations help you traverse this lattice. Okay. So, huh?
You didn't define what the partial order on rotations is.
There is some partial order. So there exists a P, given LA, there exists a P.
So there's no natural interpretation for.
Yeah. In fact, P and R can be found in polynomial time. There are natural interpretations. Basically, if you look at m naught, the first set of rotations will be all the ones that
I see.
you can go to from m naught by means of one rotation. Those will be one single rotations. They'll all be at the top level, because you should be able to apply any one of them without applying another one,
Okay.
and then so on. Sorry, yeah. Somebody else had a question? No. You're not happy, Venki?
From thinking. I'm becoming unstable.
Huh?
I'm becoming unstable. No, I'm trying to rotate all of them.
You should be full of joy and stability.
I know. After this, yeah.
Okay. Okay. So how are we going to use these facts? So let's go back to our problem of robustness and look at the.
I have a side question.
Yes.
This notion of random posits, do they make sense here?
Random. No, nothing's random.
Okay.
So fixed and deterministic and very pretty. So but you may study random also among the hundreds of things that can be done here.
Because these actually have efficient algorithms.
Yeah. I mean, there's no end to how many things can be done. So let's go back to notion of robustness. And what are some simple changes in the instance A that you would like to make? Very simple. I almost gave one of them away.
You could transmute like two people in one preference.
Right. So you could just take two in a girls list. You can take two adjacent boys and flip them.
Change her mind? Yeah.
Huh?
She changed her mind.
Yeah, she changes her mind. And there could be reason for that. Huh?
Yeah, okay.
Because you know that I don't know. Suppose the convention is to find a boy optimal marriage. So the girls are getting the worst possible deal. Why would they not flip around and try to
Yeah, sure.
get a better mate out of that bad algorithm, right? And people have done that. I mean, I don't know if girls have done that, but people have done research on that. So you may do what we can call a flip, but we'll do something more general. We'll take a girl's list. So a girl's list is something. Okay, B1, B2 to BK, and B, and something. And K is arbitrary, and move this boy up here. This is called a shift. And you can do polynomially many shifts on this girl, and n times that on all girls, and then twice that on all girls and boys. Okay, you could take a boys list and move her up. Okay, so you can apply So this is a polynomial sized domain, and B is polynomial sized, right? So for this set of errors that can be introduced to get to that instance B, one such error, I'll show you how to, what it takes to get a, I'll show you the algorithm that gets you the robust stable matching, the one that maximizes the probability of being stable for the instance B that's obtained by Bob. Okay? And we'll use all of this structure here. So,
Sorry.
yeah,
So we're only allowing one shift?
just one shift.
Okay.
Yeah, I mean, and among those 1 hour of discussion, add 2 shifts, 5 shifts, so on and so forth. I'll raise my hand there. I don't know what to do, but everybody.
So basically, you want a matching that's robust for that's stable for the given instance,
And has the highest probability of being stable for the obtained instance. And then, of course, you're given a probability distance, P probability on D, discrete probability distribution, arbitrary, sampleable polynomial time.
Good one. But given as an algorithm.
Sorry?
But given as an algorithm to you.
The
Just get
probability
explicitly
distribution,
increased.
oracle, whatever.
or it's given as a table, right? Because
Whatever you
Because
want.
there are
Yeah.
only ends.
You can write on a piece of paper and give it to me. So, how should we attack this problem? Okay. So basically, there are 2 things going on here. You have instance A, and then from that you flipped one, and you got instance B, and this is the lattice of A, and then this is the lattice of B. This is the stable matchings of A. This is the stable matchings of B. And let's say that MA intersection B will be MA intersect MB. These are the matchings that we are really interested in because these are going to be stable in A and B both. And let's say that MAB will be MA minus MB. And of course, obviously, MA is partitioned into these 2 sets. MA intersection B and MAV. Right? Turns out, both of these are sublattices of MA, of LA. These are both sublattices of LA. Not that LA, this LA. Right? That's a very beautiful property, right? Okay. So just to take things one level higher, what I'm trying to do here is I'm looking at 2 nearby instances which differ in only 1 shift, and I'm trying to infer properties of the lattices of these 2 instances. Okay, I've never seen that in any of the papers I've looked around, and that's one combinatorial thing that has not been explored about stable matchings. I mean, it's an opportunity to go further into this. So there's so much structure known, but nobody has explored the relationships between lattices of nearby instances. So, and I don't think that that we have. I mean, there's a lot to be done here probably, and given all the interest in matching markets, the deeper we go into these properties, the more we have, the more we'll be able to apply into the real world and so on, I think. Okay, so how are we doing on time?
15 minutes.
Question.
Yes, sir. Yes, madam.
Is this one of for B obtained by a shift?
By shift only. This is arbitrary B. If you take any 2 instances A and B on the same n by n n boys and n girls, then the intersection of MA and MB, that it will be always be a sublattice of LA and LB. It's very easy proof. This is the interesting fact. And because of this, it turns out further that there are two rotations in P, okay, such that M of S is stable for MA intersection B if and only if rho in is in S, then rho out is also in S. Okay? So take a closed set S in P of P, the P being the partial order of rotations. Then the matching defined by it is in the intersection if and only if whenever this rotation rho in is in S, rho out also must be S in S. Okay, so the only case that fails is that rho out is in S and rho in is not in S. Okay, and that's enough to give us an algorithm. Why? Because we'll first write the following integer program. Okay. So suppose that we have a bunch of instances. So let's say that B1 through Bk are the various B's that could be obtained by shifts, right? These are all in this domain D, okay? And then P1 through Pk are these probabilities assigned to them. Then what you do is you minimize summation Pi x I, let's call it, where, okay, so, sorry, so this is the integer program. I've started it on this side. Okay, what is the integer program has a variable y rho for all rho in R. Okay, that's an integer variable, 0, 1 variable. And whenever you have an edge from row A to row B in the partial order, then you just say y row A is less than or equal to y row B. Just put on all of these corresponding to the whole partial order. And for each of these, you let xi be at least row out, y row out I minus y row in of I. That's it. And then the set S, which is all row such that y row is set to 0. If you said let this be the set S, then the matching generated by S is in MA intersection B. Okay, that's the integer program. So it's easy to see what I mean. Okay, so there is an integer program. Now you just relax this integer program. Just let y rows be in 0 to 1, and then it has integral optimal solutions. The LP has integral optimal solutions. We can show that. End of story. So in polynomial time, we can get that matching which has the highest probability of being robust, which is robust rather, highest probability of being in stable for B. That's the first theorem proof. Okay, so let's go to the second theorem. So obviously this is too restrictive, right, Venki? So obviously this is too restrictive. We'd like to expand the domain. Yeah.
You're only allowing one.
Well, we'll still allow only one. The two part has to be done from scratch. Okay. We'll
Why you say it's too restrictive?
Because you're only allowing shifts. You'd like to allow arbitrary permutations, and we can. But we have to go to the stronger notion of fully robust. So the theorem 2 is about,
This particular thing, a little confused. So To the interior program.
Yeah.
But
No, we can
to the linear program.
relax it to linear program, solve it, get a corner solution, it will be integral.
No, I mean like
0-1 solution.
round it up and round it down. No.
There's no need.
You can always get a,
Automatically constant.
in polynomial time, you can get a corner solution. If the polyhedron is integral, has integral vertices, you can get it. So, then we take D to be, take any boy and permute his list arbitrarily, or take any girl, permute her list arbitrarily. And that's 2n times 2 to the n. All of these are possible errors that could be introduced. But there are too many errors, so we take any arbitrary subset SD, D sub S, okay, polynomial sized, and we can get a fully robust stable matching. One that is, if there is one, okay. So that goes further into this business of finding the structure between two related instances, okay. So yeah.
Any rotations?
Because every boy-girl pair can appear in only one rotation. So the set of rotations is only order n square. And your partial order is on those set of rotations. It's bound to be small. Okay. Questions, Simina? Okay. So
Same algorithm.
huh?
Same algorithm.
No. More structure. So actually, we tried very hard to go from here to somewhere until then we said, okay, what's happening here is that your MA is being partitioned into two sets, obviously the obvious two sets, which both happen to be sublattices of LA, right? So let's take this abstract case. We don't know of other errors where we can get an algorithm, but suppose somebody told us, oh, you know, B is such that L1 and L2 are sublattices of LA. Can you deal with this case? And the answer is yes. Okay. And what is needed there? So what is needed first of all is that there will be some partial order P1 for this lattice, sublattice, and some partial order P2 for this sublattice. How do we get a hold of these partial orders? Right, that's the first question we faced. Right? So in general, so you have a lattice L and some sublattice of L. What is a sublattice? It's a subset which is by itself a lattice. And L is L of P, and the question is, how do you find, so from P, obtain some P prime such that L prime is L of P prime. What is that? Okay. And then we got a generalization of Birkhoff's theorem. Okay. What's the generalization? You list out all the sublattices of L. You list out all the compressions of this partial order. I'm defining it in a minute. What's the compression? You take your partial order, add a special vertices S and T to it. S is the highest vertex, so S goes to the topmost guys, and T is the bottommost guy. That didn't change anything except that now there's a definitive top and bottom. And add an arbitrary set of edges to P. Okay, these always were in red whenever we were working on this problem. So, and then
That's crucial, right?
very crucial to keep it in red. And now you might have created cycles. This is not a partial order anymore. So you find strongly connected components. shrink them, shrink strongly connected components to get P prime. Okay. In this, S will become some A sub S, some set A sub S. It may shrink into, and T will become some A sub T, and so and each of the and the partial order will be over some partition of all the of R, right? So this will be over some partition of R, and these we'll call meta rotations. Okay, why meta rotations? Will come in a moment. On meta rotations. So this will be a partial order. That's P prime. And that's a P prime on some partition of rotations into what we call meta rotations. And what is a meta rotation? These meta rotations. So just like rotations help you traverse L, meta rotations will help you traverse L prime. Okay, so here's this L, and there's some sublattice here L prime, whose elements are I don't know where.
So you do many rotations.
Huh? So you have to apply. So first of all, when you go from M0 to the Boy optimal marriage in this sublattice, you'll apply A sub S.
So the order doesn't matter now?
Always according to the
Now we have a strongly connected component.
huh?
Now we have a strong.
Yeah, but apply within it. Apply the rotations according to the
original
P.
order,
Yeah,
not
according to the P. Yeah, because in a sense you're still in this lattice.
right.
So you go in all possible ways, applying A sub S here, and then you go within these. You may skip. Not everything here will be in the sublattice, but you can traverse, and then from here you'll go through A sub T. Okay. And so, what's the theorem? The theorem is that that there's a one-to-one correspondence between these sublattices and these compressions, such that if L prime corresponds to P prime, then L prime is isomorphic to the lattice generated by P prime. Okay, so the closed sets here will be sets of meta rotations. Okay, so we proved this theorem and we got this notion of meta rotation, and then later we found out that it's been done in what field now? Category theory. Okay, through means of category theory, which for me are obscure, but some people love it. But we were happy to get a combinatorial proof through the structure of stable matchings, because otherwise there was no way to glean from that, for us at least, this notion of meta rotation, which is critical. Okay, so now coming back to the main story, how are we going to deal with exponentially many changes? Well, so I started on that already. So basically assume that MA is partitioned into two sublattices, the intersection and the difference, and we can obtain the set of edges that defines P1. This is what we'll say, that E defines P prime, and the set of edges that defines P2. Okay, we can find those in polynomial time, and then we want to characterize what do these edges look like. Well, it turns out that there's a E is not unique, as you can imagine. Different E's can give you the same P prime, because you're compressing things and you can put big useless edges or whatever, right? So, but there is a canonical pair E1, E2. Okay, what should it look like? What should it look like? I'm going to see if I can extract the answer. So basically, look at this partial order. The partial order, huh? For 5 minutes, right? Yeah. So look at this partial order where we have put S here and T here. But this is the main thing is now. So far it was just introduction. So basically here's this partial order, right? Right? And oops, I drew it in red. Sorry. So there's this partial order, S and T, the partial order P, and then we have added some edges E1, wherever they are, and some edges E2. And we want to know what's the canonical set of E1, E2. Now, when does a set, so if I take a S which is closed, a closed set for P, okay, when is the matching generated by S in L1, and when is it in L2? L1 and L2 are partitioning all the matchings of LA. When is this matching going to be in L1? When is it going to be in L2? Well, if this set S is such that it crosses some edge E1, then obviously this set is not going to show up once we collapse, this strongly connected component. Because once we collapse this strongly connected component, the sets that will show up will be either those or those. But this set, which goes through the strongly connected component, is not going to be in L1. So if a set S crosses E1, then then MS will be in L2. If S crosses E2, then MS will be in L2, right? And every set has to be in either L1 or L2. So what's the most beautiful way of thinking about a canonical E1, E2? Oh, sorry, these edges are added. The added edges obviously go against the partial order, because they are crossing. They have to cross in the wrong direction, right? These are let's say E1. These are some E2. This is also E2, and this is E1, let's say, and this is E1. Okay, so they go against the partial order. Otherwise, they are not useful. Huh?
G to F.
You are a Paul Seymour student, right? Yes. It will be a path from T to S, alternately consisting of E1 and E2 edges. And then if S crosses like this will be in L2, this will be in L1, this will be in L2, this will be, okay? And having characterized this canonical path, we can also find E1 and E2 in polynomial time. So we were very happy. We said, oh, there's a super nice case beyond shifts that can be done. But we couldn't find any closed form way of describing that set. So then we say, okay, we have to go to all possible permutations. Okay, so all possible permutations has a big problem. The big problem is that if you look at MA, which is MA intersection B and MAB, A minus B, this thing is of course a sublattice. Okay, this thing may not be a sublattice. Okay, but this thing will be a join semi-sublattice, which means that two matchings M1 and M2 have a join but no meet. Okay, if they had a meet also, it will be a sublattice. Okay, so it's a joint semi-sublattice, and using this fact, what we can show is that, so basically we want the set of edges E1, let's call it E, which defines the P prime such that L of P prime is L1, right? What does that set of edges look like? First, we need to know what it looks like before we can find it in polynomial time. And we know what it looks like. What it looks like is that there is a path from T to S, okay? And on this path, there are red edges that sit like a flower here. And these are the edges of E, and this we call a bouquet of flowers. And that can be found in polynomial time. Okay. So if you can find this in polynomial time, you take your P, add E, obtain P prime, find closed sets in P prime, you've got matchings in M, A, intersection B. Okay. But you don't have just one B, you have many B's, polynomially many B's. So what should you do? Easy, because you have polynomially many B's, B1 through Bk. For each one, find the set of edges that defines their partial order of the sublattice, intersection sublattice. Take your partial order, add all these edges, and obtain a new partial order. And S is any closed set in P prime, then M of S is a fully robust stable matching. End of story. It's only scratching the surface, honestly. I don't know where all it can go. I mean, right? I mean, stable roommates, partial lists, 2 errors, all the things that Venki wanted to do.
Is there any notion of some person liking that the list, she likes the first person more than twice just the second person?
There's no, it's
Yeah.
yeah. But those are different notions. I mean, the pristine notion is this one. You can ask Irene. She's an expert on all of these questions. Or no?
I wasn't going to ask.
Sorry?
I wasn't going to ask.
Aren't you the expert on stable matching?
No.
Okay. Irene is. Okay.
All right.
Thank you.
Thanks.